Hello everyone, welcome to Electronically Connected. Today we're going to talk about semiconductors. Semiconductor has a property between an insulator and a conductor. Let's see what an insulator is. Insulators are non-metals. They do not conduct electricity. For example, sulfur, whereas a conductor are generally metals. Metals, for example, zinc and aluminium, they conduct electricity. Semiconductors are metalloids. They conduct electricity, but the value of electricity conducted is less than a conductor. For example, silicon and germanium. There are ways in which we can increase or decrease the conductivity of a material. For silicon, if we increase the temperature, the electrical conductivity of the material also increases. Whereas for zinc, if we increase the temperature, the electrical conductivity decreases. That means silicon works better at high temperatures, whereas zinc works better at low temperatures. Now, let's see if there are any other ways in which we can increase or decrease the conductivity. Another way of increasing the conductivity is by introducing impurities in the material. The process of introducing impurities is called doping. To understand doping better, let's first understand the lattice of a silicon. Silicon belongs to the group 4 of the periodic table. That means it has 4 electrons in its valence shell. To form a covalent bond with an adjacent silicon atom, it requires 2 electrons to form a covalent bond. As all the 4 valence electrons are in a covalent bond, this is a pure semiconductor. A pure semiconductor is also called as an intrinsic semiconductor. It does not have any impurities in them. Another type of semiconductor is an extrinsic semiconductor. An extrinsic semiconductor has small quantities of doping in them. Let's start with the lattice of silicon. I have doped this with phosphorus. Phosphorus belongs to group 5 of the periodic table. It's called a pentavalent because it has 5 electrons in its outermost shell. Out of the 5 electrons, it takes 4 electrons to form a covalent bond with its adjacent silicon atom. But the 5th electron is an extra electron. This electron can move from one place to the other. This contributes to the conductivity of the material. As we have an extra electron, the charge carrier in this type of semiconductor is an electron. A semiconductor material with p-type of doping, that is, a doping belonging to group 5 of the periodic table, is called as an n-type semiconductor. Another type of an extrinsic semiconductor is a place where we dope the semiconductor with a material belonging to group 3. Let's take boron for example. Boron is a trivalent element. That means it has 3 electrons in its valence shell. Using these 3 electrons, it forms a covalent bond with the adjacent 3 atoms. But the 4th silicon atom is left unbounded, and hence a hole is formed. This hole leads to the contribution of conductivity. The charge carriers in this case are holes. Such kind of semiconductor which is doped with an element belonging to group 3 of the periodic table is called a p-type semiconductor. So we have a p-type semiconductor which has elements like boron, a trivalent element, and an n-type semiconductor which has phosphorus, arsenic, which belongs to group 5 of the periodic table. Let us understand a bit more about the energy levels with the help of the band theory. We know now that there are 3 types of semiconductors: an intrinsic semiconductor, an extrinsic semiconductor, where we have an N-type and a P-type. The band theory has two basic bands in it, a conduction band and a valence band. Conduction band represents the number of electrons in the semiconductor, and the valence band represents the number of holes in a semiconductor. The probability of occupation of the energy level at zero temperature is called Fermi level. In an intrinsic semiconductor, which is a pure semiconductor, the number of electrons and the holes are equal. Hence, the Fermi level is present at an equal distance from the conduction band and the valence band. Coming to the extrinsic semiconductor, for the N-type, which is doped with phosphorus, that is a +5, we have 5 electrons in the outermost shell, so we have an extra electron. The band theory for an N-type semiconductor is that we have an extra electron in its outermost shell, so we have more electrons in the conduction band compared to the electrons in the valence shell. The probability of occupation of energy level by the electrons in the conduction band is more than the probability of occupation of the energy level by the holes in valence band. Hence, the Fermi level is closer to the conduction band. For P-type, which is a semiconductor doped with boron, a trivalent, we know that there are holes present. That means the number of holes are more than the number of electrons. For such cases, the probability of occupation of energy level by the electron in the conduction band is less than the probability of occupation of energy level by the holes in the valence band. Hence, the Fermi level is closer to the valence band because we have holes. Now let us see what will happen if we combine the P-type semiconductor along with the N-type semiconductor. So here we have the P-type semiconductor and the N-type semiconductor. This is a junction between the P-type and the N-type. This is called a diode, also a PN-Junction. The P-type is called as an anode and an N-type is called as the cathode. When the voltage of the P-type is more than the N-type semiconductor, then the diode works in forward bias and there's flow of current. However, when the anode voltage is less than the cathode voltage, the diode works in reverse bias and there's very little flow of current. We will discuss more about the PN junction in the forward bias and reverse bias working in the next video. Thank you. Please subscribe to my channel. See you next time.